Okay, folks, here we go. This is a quick lesson on salt. And what a salt is from a chemical standpoint is something that is neither an acid nor a base. So in previous lessons, we talked about one definition of an acid is that it releases hydrogen ions into solution. It's really corrosive on metals, produces hydrogen gas, nasty stuff. Its opposite counterpart, a base, releases hydroxide into solution. And hydroxide is caustic. It burns. It's the stuff you find in Drano or liquid plumber, and it dissolves organics quite efficiently. As I said, it does burn. It's a caustic burn. It doesn't produce hydrogen gas upon exposure to metals, which is why we use it in oven cleaner and cleaning grills and things like that. Okay, so how do you get salt? Well, there's sort of a famous rule which says acid plus base gives you salt and water. And I'll just sort of highlight that rule here, right? Acid and base gives you salt and water. And that's what happens when you neutralize. So let's take this a little bit further now. I'll just switch my pen color back to annoying red. Gotta love that color. So I'll show a quick neutralization reaction here because I had prefaced it. So if you took, and I'm just for want of space here, I'm going to take hydrochloric acid and I'm going to combine that with sodium hydroxide. And this will produce salt. And why is that? Well, here's a quick reason. And I'm just going to do a little highlighting on this. Let's choose sort of maybe a lighter green. There we go. When we look at what is going to happen, right, our hydrogen is acting in place of a metal here, and it's going to combine with hydroxide, which is a negative ion, acts as a non-metal. And if we give our other counterparts just a quick view here, go with purple, this sodium is going to want to react with its non-metal counterpart. So what do you get? It's called a double replacement reaction. And the end product is going to be HOH. That's one way of writing water. But if you write it, you most often see it this way. And you get what I like to call NaCl, NaCl. Now that is salt. And that's water. So when you take an acid, a known acid here, and combine it with a known base, what happens? The general rule, the formidable rule, is that you get salt and water. It might not be the salt that you expected, right? There's other salts out there. There's iron 3 chloride. There's copper 2 chloride. So because a salt is anything that doesn't have the H and the OH in it, it is a different thing. So you get these products, salts, from neutralization reactions. You can also get them under some different conditions when oxides or carbonates react with acids, or when metals react with acids. But I'm going to focus on neutralization here, okay? Table salt, the garden variety NaCl, that's in our bloodstream at 0.9%, right? So if you look at an IV bag, you'll see 0.9% NaCl, okay? And that's good. That's about what our natural sort of saltiness should be. You'll see salts in places where things like seawater, salty lakes, where there's really strong salt deposits. And once the water is driven off, you will see that what you'll get will be a sort of a salt deposit. And that's what you're seeing down here in Death Valley, right? Now in salt, you'll also notice that they'll say that salt has been iodized. A little reference to this point here. And we've added salt because you can get a lump on your throat developing when your thyroid gland becomes enlarged. And if you don't get enough iodine, that's a problem. So they added it to salt to help avoid this disease called goiter. Salt is found in a lot of things like batteries, explosives, fertilizers, vitamins, and in us. It's really important. It's in batteries because it is an excellent conductor of electricity, and we need those electrons to move around. Okay, so like we say, sodium chloride is only one kind of salt. Now, in these reactions, we were talking about carbonates a minute ago. So when we look at a carbonate, and here's the carbonate portion right here, when it comes together, you are getting a neutralization. This hydrogen is going to make its way to that hydroxide, and they cancel each other out. That's why water, pure water, has a pH of 7. It's completely neutral. What that leaves behind is these ionic little doodads, right? There's iron and there's the carbonate, and this is a kind of salt. It's an odd-looking salt. You're thinking, where's the chloride? In this case, it's not a chloride-based salt. Go to our second example. Now, these are balanced equations. The magnesium had to buddy up with someone in this double replacement reaction, this special double replacement reaction that's a neutralization reaction. What do? You get magnesium carbonate, and there it is. Okay, so you might be catching on to this now. If you keep your eye on the neutralization, right, that will give you your H2O. Okay, so 6 molecules of water, and then the calcium has to go with the phosphate. So calcium is a 2+ ion, and phosphate is 3-. So if you look at the formula, we needed, just a reminder of ionic balancing here, we needed 3 phosphates to give us 6+ strength, to cancel out 2 phosphates, 6- strength. They're attracted to each other, and they form a very strong ionic bond. As a result of this, because this is a strong ionic bond, salts have a very high melting point and a very high boiling point. They're ionic. They're so glued together that they don't even want to change phase. All right, so what's our last one? Our last one is sodium phosphate. Why do you need 3 sodiums? Just a reminder, sodium is a group 1 element, right? And we call those characters in the first column, right? We call those our alkalis. And then beside that are the alkali earth metals. So they like to donate electrons. So they're really interested in these ionic bonds. There we go. Okay. You might notice above here, when you look at this and you're saying, self, what's going on there? When electrons have been exchanged, when you draw we were doing this with Bohr diagrams, and now we're sort of looking at the Lewis structure, which is the outer electrons, right? Because sodium gave up its outer electron, you don't have to draw its inner core. You just say their sodium is a +1 cation, and that electron it gave is there. So when you draw ionic compounds, you'll notice that these brackets are here, and these brackets are around the chlorine. You don't have around the valence shell to show that an electron has been, well, in this case, accepted, right? So we're showing them glued together with these square brackets. Okay, so metal oxides are some pretty interesting things. Metal oxides happen when you burn metal. So a famous demonstration is to burn magnesium ribbon, and you get this magnesium oxide stuff. And what happens when you burn magnesium oxide, right? This guy right here, this is a metal, and this is oxygen. So we call it a metal oxide. You really don't want to put these in water, because when you look at the neutralization reaction, what's going to happen, right? So if I write water this way, you're thinking, oh, okay, what's magnesium going to do? It's going to take hydrogen's position, right? It's going to sneak in there. What's going to happen with magnesium hydroxide is that is going to be a strong base. And what bases can do is they will put these ions in water. And that's not good, because now what you've got is you've got magnesium hydroxide. If I said you would put sodium hydroxide into water, you'd be like, that's a terrible idea, because it raises the pH of the water, and that'll kill a fish. So If you put aluminum into water, the aluminum is going to find its way to the OH part of water right there. So you get aluminum hydroxide, not good, strong base in water. Sodium oxide is going to do the same thing, and it will find its way to the OH in water. And calcium will do the same thing. So you have some pretty strong bases. We see magnesium oxide, right? You can burn metals. They will burn. There's aluminum oxide. And so you have to be pretty careful with your metals, right? Metals can naturally form oxides upon exposure to oxygen in the air. And then you think, okay, I've got a metal oxide. So you had better not store these near water, because they'll form really strong bases, and that's important with where you put your chemicals in the chemical closet. This has a lot of consideration. It also means you don't ever want to let the industrial pollutant of a metal oxide get into the water. It will, especially in fresh water, it will devastate fish. So, non-metal oxides, a couple of examples here. Non-metal oxides are different. If metal oxides make bases in water, what does their opposite do? Well, if we're talking about non-metal oxides, you think about non-metals, right? So basically covalent ones. Oop, happens to shift that. Oop, just restart that. Okay, so here's carbon dioxide, right? And it's a covalent compound. So look at all these oxides. There's nitrogen, that's not a metal. There's sulfur, not a metal. And there's phosphorus. So if we do the math on these and we say, well, what's going to happen? Think about H2O, right? I like to write it like this because it makes that hydrogen really available. What will happen is that hydrogen will move into a relationship over here. So what do you get? You can get nitrous acid. You can get nitric acid. Think of it as the acid that can form, but you'll notice there's a 3 here and a 2 here. These are just two variations of the nitrous acids that you can get. Okay. This one's a little bit more clear. If you look at water in this circumstance, right? The hydrogen from water, right here, can get in front of our friend over there. Remember, there's a lot of water. We're not talking about every water particle. But if we get some forming H2SO3, sulfurous acid, we've got acid rain. And the same with these. These are aqueous. So you're getting nitrous and nitric acid coming down from the sky. This isn't good, right? So if metal oxides make bases in water, non-metal oxides will make acids. It's the opposite. What's interesting is carbonic acid, right? You'll find that in soda. And when what happens is they pressurize carbon dioxide into water and they form carbonic acid. And when you pop the top on a can of soda and you decrease the pressure, all that carbon dioxide comes bubbling out. It was put in under pressure, it comes out under pressure. So this reaction is an interesting one. They do it because what it will do, that reaction can actually go in that direction. If it was created under pressure, then releasing the pressure can kind of bring some of the carbon dioxide back. And it makes for a great soda. You can see why soda is not good for your teeth, right? Carbonic acid, right? Not good. If you look at diphosphorus pentaoxide, that makes phosphoric acid. So again, these are really strong. You notice here with these sulfurs, right? These are, sulfur is something you really got to keep a hand on. Why? Well, if you kind of take a look at the sulfur cycle, right? I'll just sort of zoom in. If it gets up into the rain, you've got sulfuric acid's coming down. It's doing a number on plant life and things like that. And it's not good. You have sources of organic sulfur, right? And there's a bit of a sulfur cycle that naturally goes on. But if you're releasing from a coal-powered plant or from diesel vehicles, you might have noticed that if you go to the pump that says low sulfur diesel, there's a reason for that, because it was contributing to acid rain. Here's the slide on acid rain. It devastates forests. It changes the pH of the soil by lowering it. It does a number on the famous monuments of history. If you get acid rain, you could get acid smog, and that caused health conditions in places like the UK. So when you were burning a lot of fossil fuels, making a lot of non-metal acids that were in the air, it was just having a tremendously brutal effect. Here you have your sulfur oxides becoming sulfuric and sulfurous acids coming down. And then they say NOx because there's different forms, right? There's NO2, that's nitrite, and NO3. And these combine with rain, right? And they come down as nitric acid. Now you might say, oh, it's kind of dilute, but if you take a peek at this and you say, well, they're getting carried by the wind and they're coming down and they're literally dissolving buildings. So we had to get this under control because these acidic non-metal oxides were just doing a number on everything. Here's some more, right? And the smokestacks that you see here were actually designed to be tall enough to get the pollutants to go further away from the town, sort of on the prevailing wind currents. Again, not super great. Okay, so what happens when you put metals into an acid? Deep thoughts. Well, it's kind of interesting. When you take something like hydrochloric acid and combine it with zinc, you're going to get a single replacement. Essentially, zinc is going to butt in on its corresponding metal, in this case, the hydrogen. So you get a single displacement reaction. So there's your zinc chloride, and here's your hydrogen gas. So this is what acids do. When acids are added to metals, the hydrogen gets bumped out, and you get a flammable gas. Right? You can run on hydrogen gas. You can run vehicles on this because you can combust it. It's very powerful. It's how we get off the planet with the space shuttle. So keep your eye on what happens. Each time when you add an acid to a metal, the metal takes the place of hydrogen. So that's aluminum sulfite and hydrogen gas. Here we go again. Magnesium moves in on the hydrogen. You got magnesium phosphate and hydrogen gas. Well, stop for a moment to think about what's going to happen with this, because that aluminum wants hydrogen spot. So you're going to get aluminum chloride, and you guessed it, hydrogen gas. So you can see the effect in this reaction here with what is happening. Copper with nitric acid. Oh boy, you're going to get several products. You're going to get the salt. And I know you don't think about salt, but that's not an acid or a base. You're going to get some nasty gas, right? This gas here, and you're going to get some water. So some of the reactions aren't as straightforward as the ones above, but you can see this is not something really that you want to mess with. Dipping copper into nitric acid will give you a pretty nasty gas and a form of salt you had never thought about. Or maybe did. Who knows? Carbonates, when they come with acids, they neutralize. So here's calcium carbonate being written over here. That's what it actually looks like. So carbonate rock is, if you sort of look at carbonate, you think, well, it's pretty close to CO2. And you say, well, okay, if carbonates come in contact with acids, let's say we'll pick sulfuric acid, right? It's going to do a number on that. So what happens? We're looking at a double replacement reaction. Calcium, right? Calcium is going to find, it's a cation, so it's going to find its corresponding anion on this side in the reactants. So you get calcium sulfate. You also get you've got calcium sulfate, and you have some leftovers. You can still see that you've got this, right? So what can you get? When you think about every science fair you ever went to, when they added baking soda and an acid, you get the fizzy bubbles, right? So when you have carbonates and acids, one of the things you got to be aware of is it is going to neutralize. So you have your salt here, you get your water, but you always get fizzy bubbles. And this is what makes, well, carbon dioxide in this case. This is what made the bubbles when you drop the vinegar right here onto the baking soda. And then that has an expansionary effect, and you put some dye in there and maybe a little bit of soap, and it looks like lava running down the hill. Every science fair always has a volcano, and I love it. Think about what's going to happen here. You're going to get a salt, right? So calcium's going to seek out the opposing polyatomic ion on the other side, the other reactant. So our cation has found our anion. So we get salt, because this is not an acid or a base, folks. And then you get water. And oh, look, carbon dioxide bubbles. You start to see the pattern. I'm going to get calcium, do something with chlorine, calcium chloride. Hey, there you go. And water and bubbles. Lithium is going to have a field day with bromine, right? So we get, shrink this down. Here we go. Oh. Every time I change the screen size, it tries to freeze up my work. I keep forgetting that with PowerPoint. Okay, so here we go. The salt is lithium bromide. It's aqueous because it's dissolved in some water. And there's water and there's carbon dioxide. So there you go. Forms of salt you didn't think about. Just pay attention to the fact that you get the extra little bit here, the carbon dioxide. And it's just patterns in chemistry you can set a clock to. Very exciting. Okay, so the very last slide talks about reactivity of elements. Like, why are things so reactive? And this is kind of a Chem 11 topic, but I can tell you that fluorine is in this position, right? And if you come over here, there's lithium in that position. And you wonder, why are you pointing this out to me? Well, what happens is, as you go in this direction, right, you're heading towards the nonmetals. And as you go in this direction, you're heading towards metals. Okay, that makes sense, because there's a dividing line somewhere over here, right, that you've seen, and I just drew it horribly. Let's see if I can erase. There's a dividing line. Let's tidy that up, Bleeker. Here we go, right? Just doing this roughly. Kind of get this idea. One thing you hadn't really thought about, though, why are metals so reactive? And there's something interesting here. They say atomic radius. Well, that's how far out your electrons are. And the further electrons are from the nucleus, that's one of the reasons metals want to get rid of them. They're already far out. And it's not like lithium is going to get 7 electrons to get to the end of the row, the end of the period in the periodic table. So what happens? Atomic radius gets bigger as you go down and to the left in the periodic table. And elements like this, oh boy, they want to get rid of their electrons. Everything in group 1 has 1 electron it wants gone anyways. And it's way the heck out there. So when you get to things like cesium and you get to the bottom, if you get to francium, that element has that single electron is so far out, the first thing it'll do is try to get rid of it. Conversely, you look at fluorine, and fluorine has a very small atomic radius, so its electrons are super close to its protons. And remember, the protons and electrons are oppositely charged. So fluorine is tiny. Its electrons are right near the nucleus. So fluorine is not giving up electrons. It's completely the opposite of francium. Francium's got a gigantic atomic radius. Fluorine, not so much. So the most reactive nonmetal in the periodic table is fluorine. You don't want to play with that at parties. And the most reactive metal is its complete opposite, francium. Right? The metals give up their electrons because you can't pick up, multiple electrons and get all the way over to your corresponding noble gas. You just can't pull it off. So they just try to get rid of electrons because their inner core is already full. So they're willing to get rid of a partially filled outer core. Okay, so in the rest of the slideshow, there's some of these review questions. I'll leave that to you. They're just meant to be extra practice, okay? But I've gone overboard on time. I always do. So that's it. Another edition. Thanks for listening. Mr. Bleecker, out.